Hi, this is a video about intermolecular forces. So first thing, before we talk about intermolecular forces, we're going to talk about intramolecular. So intramolecular forces are the actual chemical bonds. So like the covalent bonds that we've been drawing, for example, in this picture between chlorine and chlorine. So this is the within the molecular force, which is really just a chemical bond. The word intra kind of means similar, like intramurals or between teams that are within our school. So then we have intermolecular forces, and intermolecular forces are when you look at, so here's like an ammonia, so NH3, and then the lone pair there. So then it's kind of negative, partially negative up here and partially positive there. So what'll happen is a nearby ammonia is going to be attracted. So these are not true bonds, but we call them forces, intermolecular forces. So this ammonia is interested in this ammonia, for example. And intermolecular forces are only present in the condensed state of matter, which is solids and liquids. In gases, they're not close enough to interact. So here is a little simulation that I'm going to show you. Let me see. Okay. So this is full screen. I'm going to show you. So there's the three types of intermoleculars. The strongest is only about 5% as strong as a real bond. So inter are not as strong as intra, but they're still important. They are why some things are solids and liquids at room temperature, where other things are gases because they don't have enough of an attraction. So the first one is dipole-dipole intermolecular forces, and this is when you have a polar molecule. It'll have a permanently negative and positive end, like we saw like with the PHET that we did when they were polar. So the positive end of one is going to be attracted to a nearby negative molecule end. And this is something that occurs for polar molecules. London dispersion forces are when the electrons are temporarily more in one area than another. So it creates a temporary dipole. Unlike the previous dipole-dipole, those you have a positive and a negative end of the molecule that stays that way permanently. These are temporary. Temporarily, you can see the electrons kind of moving, and there might be more negative on one side at any given instant. So then you can see where temporarily they're going to be attracted to other nearby atoms. So this is representing like a helium atoms that are intermolecularly attracted to other helium atoms. So this is like dipole-dipole, but the dipoles, the positive and negative ends are temporary. Every molecule has London dispersion forces because every molecule has electrons that can kind of move. And the bigger the molecule, the more the electrons, the stronger these are. So the boiling points of something that has like a stronger intermolecular attraction could be London dispersion. Those are going to be higher because they're more attracted to one another. So it takes more energy to be able to get them to go from liquid to gas. Hydrogen bonding is the strongest. It's like a dipole-dipole, but it's an extreme case of this. Water is an example of a substance that has hydrogen bonding. And I'm going to stop there. We'll go into this in much more detail. So the little simulation kind of got us looking at these three types of intermolecular forces. So let's talk about each one. So I did talk about them, but here it is officially. So a dipole-dipole is when you have a polar molecule and it's attracted to a nearby polar molecule. And you can see in the picture here, it's the negative end of the one that's attracted to a positive end of another. So this is, sometimes we use dotted lines or dashed lines. It's not a true chemical bond, but that's what the dipole-dipole IMF, sometimes we say IMF instead of intermolecular forces, that's representing that. So dipole-dipole is kind of interesting because you can look at what an effect it does have. So for example, if I look on this chart, which is in your book, at chlorine, and that would have would not have dipole-dipole because there's no permanent polarity in that. It would be a nonpolar molecule. And then if I compare that to this ICl, which would be an iodine with a chlorine, and I drew that here and I showed you the electronegativity of chlorine is 3.0, iodine is 2.5. So it's a 0.5 difference. So there's a permanent dipole towards the chlorine. So if we drew a picture, it would be permanently negative over here and positive over here. Versus the chlorine, there's no dipole, there's no accumulation of charge. So look at the boiling point. So to boil chlorine, it'll become a gas at negative 34 degrees Celsius, whereas this iodine with chlorine will boil at 97 degrees Celsius. So that's actually close to the boiling point of water. So it's pretty high compared to just the plain chlorine. So dipole-dipole interactions, those attractions make for higher boiling points. Hydrogen bonds are just a special case of a dipole-dipole, and this is an extreme dipole where you have hydrogen, which only has that one electron to kind of have pulled away, which really exposes it and makes it very positive. And the ones that the hydrogen has to be bonded to, these are your most electronegative elements on the periodic table. They're on the top right. I call them NOF, NOF, nitrogen, oxygen, fluorine. So it's poor little hydrogen with one of these really highly electronegative elements, and they will pull that electron almost completely away from the hydrogen, exposing it. So this is a hydrogen bond. I don't know why they use bond, because it's not a bond. It's not a chemical bond. It's a force. So it's not as strong, but it's still really important. So here is an example of water. If I draw nearby water here, and I'm bending it, I know there's a lone pair up here. I know that this end is partially positive and that this end's partially negative. So the hydrogen bond is from the oxygen of one to the nearby hydrogen of the other. It's that negative and that positive that are attracted. So it's not a real bond, but it is really important. So for example, if you look at water, and the boiling point of water we know is 100 versus H2S, hydrogen sulfide, it's almost the same molecule, except for this sulfur is not as electronegative as oxygen, so it doesn't have that extreme dipole. So if you look at the hydrogen sulfide, it boils at negative 61 Celsius. You're never going to find that as a liquid on Earth normally. Versus water, it boils at 100, so we see it as liquid water on Earth all the time. So if it were not for the hydrogen bonding in the water, it would be a gas. London dispersion forces are the forces that are that result of that temporary dipole where the electrons just run to one side kind of, then they run back to the other. So if you look over here, it's kind of showing you the electron cloud of the iodine, and there would be this attraction then, the positive end of one to the negative of the other. And this is something that the bigger, the more electrons that are kind of rushing to one side or the other, the stronger these London dispersion forces get. So I have another little video this time to show you.
Electrons in an atom are in constant motion, but at some point in time there are more electrons on one side, creating delta negative and delta positive charges, or an instantaneous dipole. The instantaneous dipole on one atom can induce an instantaneous dipole on another atom, and they are oriented to cause an attractive force. Later, the electrons on both atoms have moved, but they tend to move together to preserve the attractive force.
So if you look at London, oh, here's an analogy. I always use this. So you know how if you've ever been on like a dolphin or a whale tour, when you see the dolphin, actually everyone runs to that side of the boat. It's kind of like that. So the electrons will rush to one side, but then, oh my gosh, there's a baby dolphin on the other side. So they'll rush to the other side. So they kind of move back and forth. So then the analogy doesn't work after that, because you have to have then a nearby boat and then the attraction between them. Statue of Liberty, if you've ever done this, went and looked at it, same thing on the Staten Island Ferry, I think it's called. I just was on it a couple of years ago. And, people are always on that side of the boat and then they switch to the other. So it's kind of like the electrons are switching. So when you look at London dispersion forces, it's this is for everything has these, but non-polar covalent compounds, this is the only kind of IMF that they have. So, but it's really powerful. So if you look at like chlorine has a boiling point of -34, whereas bromine is 59 degrees. So it's a really big difference. And that 59 being higher is because bromine is so much bigger. It just has a whole bunch more electrons. So when it does that, where they rush to one side, and then a nearby bromine maybe, has their negative over here, but it's more positive over here, that's that attraction. And that keeps bromine a liquid at cooler temperatures on Earth. The chlorine is never going to be found as a liquid in normal temperatures on Earth. Water is super cool with the hydrogen bonding. There, again, you only have that hydrogen bonding, which is not a bond, it's an IMF. Between the water molecules, you don't see it with a gas, but you do see it with a liquid, and then it really does something cool when it's a solid. And I think we all know that ice expands when it freezes, or liquid water does, which can really wreck a lot of things. I had a soda in the freezer because I wanted it to get cold and I forgot about it. Of course, it exploded and it's all over all my other stuff. And that, by the way, is not common. Most solids are more dense and will sink in the liquid state of matter because they'll pack closer together. Whereas water, the way that it forms the hydrogen bonds, which are right here in this diagram, it forms kind of a hexagon type honeycomb shape, and that expands it. So that's why our ice floats on our lakes. If it weren't for hydrogen bonding, it would sink. So now what the application of all of this is that I want to be able to look at a molecule and know what kind of IMF it has. So this is the question that I'm going to ask myself. First thing I ask, so let's say I have this molecule. I'm going to just pretend that my electrons are around the chlorines. So this is a polar molecule because it's a tetrahedron and they're not all the same thing. So I'd ask myself, is it polar? And then I would say yes. And then I have to ask myself, does it have hydrogen directly bonded with nitrogen, oxygen, or fluorine, that NOF? And then I'd say no. So then that molecule is going to have dipole-dipole interactions. So similarly, like if I do the chlorine and chlorine, we know this is a nonpolar molecule.